Hello and welcome to episode 22 of CS350 Online. I'm your host Leslie, and in today's episode we are going to continue our discussion of file systems, and in particular we're now going to start looking at the physical file system, which is how we store the actual data on the disk and how we're going to be able to retrieve it and so on. But first, of course, our OS of the day. So we finally reached, in episode 22, the part in the course where we can talk about Linux, or GNU Linux, as many also refer to it as. Now, this operating system has actually been around for quite a while. It was created in 1991 by Linus Torvalds. And I'm sure many of you know that Linus Torvalds is actually behind the creation of this. But what's kind of interesting about this story is that my understanding is Linus didn't go out on purpose to create his own operating system. He was using Minix at the time, and he was looking for a fully functional free operating system, like something he could truly modify the code, redistribute the code, and all of those wonderful things. And Minix just wasn't what he was looking for. And when he looked around for other options for an operating system, there was 386 BSD, which was going under some legal complications. Richard Stallman's GNU project, the kernel had stalled, so it wasn't quite ready yet. And so since there wasn't anything that met Linus's specifications, he went out and created his own. And of course, you can hear all about Dr. Stallman's GNU project tomorrow. Details, of course, on Piazza. Now, what Linus ended up doing is he did develop the kernel, but he incorporated as much of the GNU project, which is free software, and other GPL applications with the Linux kernel and Linux as a whole, which is why you often hear it referred to as GNU Linux and not just Linux, is because it is incorporating so much of the GNU project as part of it. So it's kind of only fair. And my understanding is Linux actually used to be called Freaks, or I'm not sure how you'd say that, FreeX or something. And some users apparently convinced him that he should name it after himself. I don't know if I believe that. For the record, I have actually met him a number of years ago. Jesus, I guess it's like 13 years ago now. So I don't know what I believe about that. What is Linux anyways? I mean, you all know what it is because most of you are using it, at least for you to submit your assignments. I mean, when I was in undergrad, it was all Solaris. But now you get to use, I think it's Ubuntu. And you know it's a Unix-like operating system. It has a monolithic kernel. So everything is in the kernel that could be in the kernel: memory management, virtual memory, IPC scheduling, file systems, device drivers, everything. And I think the bulk of the Linux kernel is actually device drivers. Like, it's millions of lines of code, but most of that is caught up in just device drivers that they have built in. But not everything is necessarily a part of the kernel. So one of the interesting things is that the graphics interface, or the actual desktop environment, that runs more as a user program than as part of the kernel. So that's kind of an interesting thing. So things like X windows aren't necessarily a part of the kernel. They're sitting in a layer above. And one of the really nice things about something like GNU Linux, of course, is the fact that this is a free operating system, so there's no legal complications. If you want an OS and you don't want to pay for it, you can just go download it and install it. But some other really nice things about this operating system, of course, is that it's a really great development environment. And if you want to change something in it, you just go change it. And that's the end of the discussion. You have the source code, so make the change. And as a result, there are many, many different distros for GNU Linux. I mean, the first distro I ever used, oh gosh, I don't even remember what it was. Started with an S. It wasn't Susie. I know that. Yeah, you'd think I could remember. I can't remember. I actually started using this in about 96, 97 by telnetting into one of my friend's computers. And then I started using it on my home computer more regularly in about 2000, 2001, where I used Red Hat distribution. And then over the years, I've actually used Fedora, I've used SUSE, I've used Mandrake, Mandriva, Kubuntu, Ubuntu, Gentoo. There's so many distros. If you're wondering what I actually use in my home right now, so I know many of you have noted that behind me I have a bunch of computer screens that are actually attached to one of my other computers, my big research machine, and that's actually running the Kubuntu distro. Because that's just kind of what I've settled on, I suppose. But there's Mint, there's just so many. And it's because you can take the code and you can do what you want with it. You can modify it. You can make it have your own look and feel. And even things like Android are actually based on the Linux kernel. So it's a very powerful operating system. So this is kind of a cool image I snagged from Wikipedia, but the reason why I want to show it to you is it's kind of reviewing some of the topics that we've already covered, like the separation between the kernel and the hardware and the kernel and the user programs. So in black in this diagram, and it might be very small for you, you'll actually see all of the hardware. And then the red is the kernel. So black is hardware and it's isolated from the user programs, these 3 layers up above by the kernel. So the kernel, of course, is running with the full privileged setting, and you can see the kinds of things that are actually part of this. So you've got things like ALSA, your sound systems. You've got Radeon and Nouveau, and those are like your graphics card drivers. And so you've got all kinds of drivers and other base kernel systems, of course, in the Linux kernel. And then sitting above that, but not in the same privilege mode, we have things like glibc, and you have also things like the X servers. And there's lots of different X servers that you can use. There's X11, which is the one that I have used for many, many years, X11R6 and X11R5. I think most people today use X.org or X free86. Those are pretty common too. Then you've got some of the window managers. I will turn up the mic sensitivity. Hopefully this is a little bit better. And then you've also got things like touch screen behaviors and such. And that's all in the layer above the kernel. And then on top of that layer, you've got even higher level things. So you've got the GNOME shell, you've got Plasma, GTK, Qt, so windowing libraries that the user would use. And then on top of that, you've actually got your desktop widgets and your 2D and media and 3D applications right on top of that. I apologize for the audio issues. My son is obsessed with coming over to my desk and pushing every button and turning every dial that he can find. So I'm trying to keep the mic in the right state, but admittedly, he keeps changing it. Now, for those of you who aren't familiar with the fact that you can actually change the desktop environment with Linux, this is Enlightenment with a black and white theme. So that's kind of fun. This one actually reminds me of one of the older window managers called TWM, and I hope that you never have to use TWM. But TWM was very similar to this, but less graphic quality. And this is an older version of KDE. It looks a little bit fancier now. And, I don't have Unity in here. So there was also Unity. And if you actually sit down physically in a computer lab at the school, you would see the Unity desktop environment. And I know you're not going to be sitting down in any of the computer labs for quite some time. It's probably going to be, well, it won't be the winter term, and I don't think it's going to be the summer term, so I actually do not know when you'll actually be able to return to physical campus. Hopefully sometime before you graduate. All right. So that's the Linux operating system. So just one more announcement I want to give before we go back into talking about file systems, and that is just to reiterate, we are going to have a guest speaker tomorrow afternoon at 3:30. And it's Dr. Richard Stallman, who is the founder and chief of the GNU Project and Free Software Foundation. And he's going to be talking about why operating systems should be free and all the software that runs on them should be free. So I'm sure that's going to be a very exciting talk. And that is, again, at 3:30 tomorrow. Now, to view the talk, we are only going to be using completely free software. So the way that you're going to be able to watch this is I've posted a link to the CS Club, because the CS Club is being ever so generous as to sponsor and actually host this for us. So I've given you a link to where you can find the live stream. The live stream is happening using WebM and Icecast. So my understanding is if you're trying to use a web browser like Opera, it may not work, and you might need to find a plugin for VLC. But if you click on that CS Club link at 3:30, you'll be able to see the live stream. And if you want to ask questions, we're going to be doing that via IRC. Now, for those of you who are not familiar with IRC, it stands for Internet Relay Chat, and I don't know how old this chat protocol is. It's really old. I started using it in 96, really long, right around the time I started experimenting with Linux. So I understand that many of you may have never used IRC before. So there are instructions on Piazza for how to access it. So if you don't already use IRC, you're going to click on the link for the web IRC client, and it's for Freenode. And then, maybe we should just show you this so you actually can see what I'm talking about. Let's do that. That's a great idea. Because I want to make sure that if you have a question, you can actually ask it. So let's open up this. Nobody needs to see my email. That's not it. Go open up Piazza. So you'll see I've actually got a link to this in Piazza. So this is web Freenode IRC client. Oh, I guess you can't see that. There we go. Sorry about that. So here you go, Freenode IRC. This is the link I have in this. So you're going to put in the nick box, put your nickname. So for me, of course, that's Lenortha. That's not traditionally my IRC name, but I'm not going to go back to my old one. Now, in the channel box, you're going to do #CSC. Click I'm not a robot, and then hit start. And there you go. It's going to actually... Here we go. We are now in the University of Waterloo's Computer Science Club room. We don't call it a room, though. It's called a channel. And so at the bottom here, you can type something, and you can see all of the lovely people who are currently in there as well. So if you join this, you will be able to ask questions, and then we will make sure that Dr. Stallman gets to see those questions. And we may not get to every question, but we will obviously do our best. And then to leave, of course, just close it. There you go. That's really all you need. I mean, there's obviously lots of other IRC commands, but you don't need to know them. There's things like private messages and all kinds of other things. But again, you don't need to do that. So don't worry about that. All right. So we were talking about file systems. And in our last episode, we were discussing the logical and virtual file system. So remember, the logical file system is the high-level API that is presented to the user. So this is things like open and close and seek and functions to change the metadata of the file. But what's interesting, why it's called the logical or a high-level file system, is because you actually don't, it doesn't tell you anything about the underlying physical file system. It doesn't tell you how the data is stored on the disk. That's all hidden from you. Like when you open a file, when you use open, you don't have to know if it's RISE-RFS or NTFS. It doesn't matter because open has abstracted that completely from you. So the logical file system is that high-level API. And then we have the virtual file system, which takes all of the different physical file systems and presents them to the logical file system as one thing, so that the logical file system doesn't have to use one version of open for the RISE-RFS system, and the user doesn't have to use another version of open for the NTFS system. So the user isn't aware that there are different physical file systems underneath. Today we're going to focus, however, on the physical file system, which is how do we actually store the data on the physical disk. So let's jump ahead to that slide then. All right. So before we talk about the actual physical file system, we need to think about what actually needs to be persistent. So remember that we talked about files having metadata and files having data. Well, obviously both of those things need to be persistent because we want the file to stay around. We don't want the file to disappear. And the metadata is important for reading and understanding that file. Directories and links, which form these namespace hierarchies, well, that's key to actually finding a file on our system. So it's very, very important that directories and links are stored persistently as well. Remember that we actually store directories as just another kind of file. Then we have the file system metadata. Now, we haven't talked about this one yet, but we will talk about it a bit more in a few minutes. But essentially what we're saying is, what kind of metadata do you need to know in order to understand how to access this file system? For example, where can I find the root? But there's lots of other information that we use with respect to file systems that doesn't need to persist. Things like the per process open file descriptor table. So the file descriptor table in each process only needs to live for the length of time that the process lives for. If the computer is turned off, the process doesn't exist, and therefore there's no point in having it. So that doesn't need to stick around. The other thing is the kernel's open file table. If the computer's not on, then it's not running anything, so there's no files open. So you don't need to do that. Other things that we don't need to keep are cached copies of the data. So because secondary storage tends to be quite slow, not just because it tends to be using mechanical hard drives, but because it's also, physically not located inside your computer, so it's on a long wire. And I mean, in my house, my secondary storage, aside from the SSD in my laptop, my main storage device is a network attached storage device, so that's even slower. For the record, I actually have it sitting on a 10 gig switch, so it's slower, but it's not that bad. So in order to improve the performance, we actually tend to cache a lot of file data so that instead of going to disk all the time, we can grab it from the cache. So the cache, of course, only pertains to currently open things, and if nothing is currently open, then there's no point in that cache persisting. So that's kind of the lowdown. Now, the one thing I want to say is this being non-persistent information is kind of a bit of an outdated claim. So this is the general claim, but if you actually look at modern operating systems, they have behaviors like sleep and suspend and hibernate and things like that. And so that's where this kind of becomes really blurry because the computer's not on, you're not actively using it, but when you open the lid back up on your laptop, you want the files that you had open in VI to still be open. So when it comes to things like sleep and hibernate, we are going to cause this to persist. Now, here's where things get interesting. So you have to ask, does hibernate just keep RAM powered? Is that all we're doing? Because then we would just keep this all in RAM. But if you're doing like some kind of deep sleep where maybe you're storing the computer state to disk, well, then you might have to save this to disk. It really depends on the implementation of that. So this here, non-persistent information, is kind of a hazy topic. All right. So, sorry, I clapped my hands together and I might have looked like it hurt for a moment. It's because it did. I was shoveling snow there a few days ago, and I hurt my one of the bones in my hand pretty bad. Of course, I forget about it, and then I hurt it again by doing silly things. Oh well. So let's talk about the disk we're going to use. So for the purposes of our physical file system, we're going to have a disk that's 256 kilobytes. I know that's really tiny. The reason why we're doing that particular size of disk is because we want to be able to show the example on the slide. And I don't want to have to draw 300,000 boxes. So 256 kilobyte disk. We're going to use it as a mechanical hard drive, moving platters and such. And we are going, you'll just have to imagine them in your head. We are going to use a sector size of 512 bytes. Remember that even though memory in your computer is byte addressable, the actual physical disk is only sector addressable. So you can't do a read or write to a particular byte of the disk. You can only actually do whole sector reads and whole sector writes. Okay, keep that in the back of your mind as we're going through this. So that means that my disk has 512 total sectors. Now, if I was doing on-demand paging, my page size would be 4 kilobytes because that's the standard page size that most operating systems use or have used. That would mean that when I need to get a page from disk, I need to get 8 sectors. And since those 8 sectors that belong to a page of virtual memory may not be consecutively stored on the disk, that could be 8 separate I/O operations. And as we know, I/O operations are actually quite slow. So what we do to improve our performance here with respect to on-demand paging and just generally trying to reduce the number of seeks we have to do is we're actually going to take 8 consecutive sectors and call it a block. So blocks are 4 kilobytes, conveniently the same size as a page. So even though the disk is sector addressable, in our file system, we're going to only do block addressing. So we're going to do things at a block level instead of a sector level. And that's going to have lots of advantages because that means you can read a whole page and it's 1 seek operation instead of 8 seek operations. So that's going to help us out a lot. That means, however, that our disk has 64 blocks, which means we can draw it. There it is, 64 blocks. There's our disk. It's so exciting, right? Okay. So of our 64 blocks, we want the majority of these blocks to actually be for file data. Now, something that might take you by surprise is that we don't actually have files sharing blocks. So if I create a file and I don't use the whole block, then let's say I make a file that's 2 kilobytes. Well, then we generally speaking, most file systems aren't going to use the other 2 kilobytes of that block for another file. It's not to say that they can't, it's just to say that our file system isn't going to do that. So we have decided anyways, that there will be 56 blocks set aside for data, which means that I can have a maximum of 56 non-empty files on my disk. That's the maximum number of files. Now, that probably seems really small or limiting to you, but if you consider the fact that the disk is only 256 kilobytes, 56 files probably is a lot. Now, 8 of those blocks we are not setting aside for data. We are setting them aside for the metadata with respect to the file system and the files itself. And those are going to be the first 8 blocks of our disk. Okay. So now we need to talk about this thing called an inode. So I need some kind of data structure that can keep track of the fact that this file uses these data blocks. And I also need to keep track of the fact that this file has some metadata, such as an I number. And this file also has a last access time and a last write time and all of that information. And what we're going to do is we're going to create a data structure called an inode. And an inode is going to contain all of the metadata for the file, and it's going to contain the mechanism that points to all of the file's data blocks. You can kind of think of it as, for now, we'll expand upon our understanding of this in a moment, it's kind of like the page table for the file. Now in our system, we are going to set our inode size to 256 bytes. And we have pre-decided that 5 blocks will be set aside for inodes. So these 5 blocks here are going to be for our inodes. So that means that we can store 80 inodes. And if you want to see what that looks like, I'm going to zoom in here. Here we go. So these are our 5 blocks. And you'll see that each of those blocks has 16 of our inodes in it. Now that is called our inode table or our inode array. And you remember how we had those iNumbers, that unique identifying number for the file? Well, we're actually going to have that be the index of your inode. So if you were file 87, that means your inode is at index 87 in the inode array. That's really convenient, right? Remember why we said the operating system would want to refer to the file by a number and not a string? Well, because now I can do a lookup in a constant time operation. We like that, right? So we've got our inode array. That's our inodes that we use to access our file data. Now here's the thing. Let's suppose I want to create a new file. There is an array of inodes. Some of them are in use and some of them are not. This is not a linked list. This is a fixed size array. Some of them are in use, some of them are not. I want to create a new file, which means I need to find an inode in the array that is not currently in use. Now, how I could do it is I could copy the inode array from the disk into RAM, and then I could search through that until I find an empty inode, and then I could write it back to disk. I could take it. You know, that probably doesn't seem like a bad idea on this disk because it's only 5 blocks. But you know, my file system downstairs, my big NAS, has 4 14 terabyte drives in it. That's my primary NAS. I actually think it has more disks than that because it fits 8 or something. I've lost count how many disks are in it. Okay. So how big do you think my inode array is going to be on that disk? Is it a gigabyte? Is it 2 gigabytes? I wouldn't be surprised if it's huge because I have literally over 50 terabytes of storage. Okay. Do you honestly, in order to find a new inode that you can use, do you want to copy 2 or 3 gigs of the inode array into RAM just so you can find a free one? That doesn't make sense. So because that would be so slow, we actually have a cheating way to actually find a free inode. And it's called using a bitmap. So we are going to set aside 1 block to be our inode bitmap. And essentially each bit is going to correspond to 1 inode in the array. If the bit is 0, it means it's free. And if the bit is 1, it is in use. So I read in the inode bitmap, which in our case is only 1 block. And that 1 block, as I read through bit by bit, will help me find a free inode. Now, what this actually means is because 1 block is 4 kilobytes, that's actually over 32,000 bits. So that means I can track over 32,000 inodes. I only have 80 inodes. So this block that I'm using as my inode bitmap is actually capable of tracking more inodes than I actually have. And of course, as part of the file system's metadata, we would say, hey, yeah, you only have 80 inodes. So don't search beyond bit 80. Okay, so that's kind of cool. Now we need to ask ourselves, so now we know when we want to create a new file, we need to ask the inode bitmap to give us the address or the index of a free inode to use. But when I start writing data to disk, let's say I actually want to save my file now, I need to find some free data blocks to store it. I don't just like pick a random data block and start writing because I'd probably overwrite an important file. Don't want to do that. So we need a way of tracking all of the data blocks that are in use and all of the data blocks that are free. Now, one of the things that you could do is you could look at each inode for every file that exists in the system, and you could go through its pointer list and find all of the data blocks that are associated and with that file. And then after you go through each inode, you would have a picture of which ones were in use and which ones are not. Seems like a really bad idea. So we're not going to do that. Another thing you could do is you could make the assumption that a free data block is all zeros, which is an assumption that you actually can't make, but let's pretend you could. And you could just start reading in data blocks until you find one that's all zeros. Again, That's a really horrible idea for various reasons. One, because empty data blocks are not guaranteed to be zeros. Two, because I don't want to read in 56 terabytes just to find the one 4 kilobyte block at the end of the array that's free. So let's use a block bitmap. Just like we had an inode bitmap to keep track of free and not free inodes, let's use a data block bitmap where each bit corresponds to exactly one data block on our disk. Again, one 4 kilobyte block on our disk is capable of tracking 32,000 data blocks, which is more than we have, so we're good. Now, obviously, if you have a much larger disk, the number of blocks you would need for the inode bitmap or the data block bitmap or the inode array is going to be different. So that's really going to depend on the size of your disk and your file system. So the question on Twitch is the bitmap related to the image of an OS? No. They call it a bitmap because it is mapping bits of data to either inodes or data blocks. So it's literally just going to be like some ones and zeros, and if it's a 0, it's free. So let's say bit 87 is 0, then that would mean inode 87 is free. So it's not an image. I mean, you could render it as an image, and I'm sure it would look very noisy or interesting, but it's not like a picture. Okay. The last block to talk about is the super block. And the super block contains all of the information about the file system itself. So it's going to tell us how many data blocks there are. It's going to tell us how many inodes there are. It's going to tell us where to find the start of the inode array. It's going to tell us where to find the inode bitmap. It's going to tell us where to find the data block bitmap. And any kind of metadata we need in order to tell the operating system how to interact with us, that's going to be stored in this super block. And so those 8 blocks on our 256 kilobyte disk, this is a close-up. You've got the super block for this file system metadata. That's usually in position 0 because it's really important that the OS can find your super block when you mount the drive. And then after that, we have the other metadata we need to actually access the data on the disk. So it's pretty cool, right? All right. So what do we do with this? Well, first off, we need to take a closer look at our inodes. So here's the thing. Inodes are a fixed size data structure, which means that we have set them to be, in our example, 256 bytes. Somehow the inode actually needs to be able to track all of the pointers to all of the data blocks. But if a pointer is going to be 4 bytes in size, then there's a very restricted number of pointers I could actually store in the inode. And if I can't store that many pointers in the inode, then my file can't actually be that big. So some people are like, well, why don't I just grow the inode? But we're not allowed to do that. So the inode is a fixed size thing. And the inode actually has to contain a lot of information, like the type of file this is, the permissions of the file. Because when I try to open a file, I need to determine if I actually have permission to open that file for reading. Do I have permission to open that file for writing? I have to check that. And the inode can actually store the information. We're going to store the length of the file, the number of blocks. We're going to store things like the last file access time, the last time we updated the inode, the last time I updated the file. I'm going to store the number of hard links to the file so that I know when nobody is referencing this file anymore that it can be deleted. And then we're going to contain a bunch of different pointers, kinds of pointers to file data. So I want to show you this picture because it's meaningful. We obviously can't store every file data block pointer in the inode. So we're going to do something a little funny. We will store a number of what's known as direct pointers. A direct pointer is a pointer in the inode that points directly to file data. And the direct pointers are going to be used for the earliest bytes of the file. So starting at byte 0 of the file data, that will be accessed via a direct pointer. If we cannot fit our file in with our direct pointers, we have use of what's known as a single indirect pointer in the inode. What a single indirect pointer does is it is a pointer to a block of pointers to file data. And this single indirect pointer block, this block of pointers, is actually occupying a data block on the disk. So this is a pointer to a block of pointers to file data. And if you still can't make your file big enough with that, there's something called a double indirect pointer. So you'll have a pointer in the inode that points to a block of pointers, and each of those pointers points to a block of pointers, and each of those pointers points to file data. And if that still isn't enough for you, we have triple indirect, which is a pointer to a block of pointers, to a block of pointers, to a block of pointers, to file data. Pretty neat, eh? So our inodes are going to contain direct, single indirect, double indirect, and triple indirect pointers. And all of the pointer blocks, keep in mind, they also occupy disk space. So they are going to occupy data blocks. They are not, these pointer blocks aren't a part of the inode array. So how do we figure out, using this mechanism here, is there a maximum file size? And the answer is yes, there is a maximum file size. Because our inodes have one triple indirect pointer, one double indirect, one single, and I think it's like 10 or 9 direct pointers. So that means that if I run out of triple indirects, like I use every pointer there, then I can't add any more data. But how much is that? So let's start the computation. So I'm actually going to make this slide smaller, and we're going to do the math in OneNote so you can actually see it working out. If you can't read the slide that well, of course, they're posted online. Here we go. You know, it just occurred to me that I don't know if there's like an always on top feature for Mac OS. Oh well. Features that KDE has that I'm pretty sure Apple doesn't. Maybe it does. I don't know. Okay. So let's start with our direct pointers. So direct pointer is a pointer right to data. And so our block size is 4 kilobytes. In our example here, 4 KB. Then each direct pointer points to 4 kilobytes of file data. To the comment on Twitch about Apple should patent the term inode, then they'd have rights to all the data. Please, no more patents. People have tried to like patent like the smiley face emoticon and like weird things. All right. So we've got a direct pointer and it points to file data. So each direct pointer gives us 4 kilobytes of file data. Now, if we look at our disk, we are saying that there are 12 direct pointers in our inodes. So to figure out how much data that gives us, we do, so for direct data, we get 12 times 4 kilobytes. So we're going to get a file that is 48 kilobytes in size. By the way, the formula here is the number of direct pointers times the block size. And this formula you can find in the file system guide on Piazza, of course. So I've got 48 kilobytes. Yeah, but see, when I take a photo, none of my photos are that small. The only files on my disk that are that small are my code files sometimes. Not always. So I need to be able to store more data. So that's where we use the single indirect. So, stupid system. Our single indirect points to a block of pointers. And each of those points to file data. So in order to figure out how much data is accessible via the single indirect pointer, I need to know how many pointers fit in a block. Like I'm scrolling and the text is like not moving. Oh. Yeah, and then it disappears. Okay. That's so much fun. All right. Single. It's to a block of pointers. How many pointers in the block? So, number of pointers in a block is equal to the block size divided by the pointer size. Now, if the pointer size is not given to you, you should always assume it's 4 kilobytes because that's standard. Or not 4 kilobytes, 4 bytes. So if my blocks are 4 kilobytes, that's 2 to the 12, and my pointers are 4 bytes, that's 2 to the 2, then I can fit 2 to the 10 pointers in a block. And this is going to be useful for our other calculations as well. Okay, so the data accessed via one single indirect pointer in the inode is, for our inode, 2 to the 10 times 4 KB, which is 2 to the 10 times 2 to the 12. So that gives me 2 to the 22 bytes. It's about 4 megabytes, 4 megs. Now, what if you had more than one single indirect pointer? The general formula is number of single pointers in the inode multiplied by the number of pointers in a block multiplied by the block size. And again, I know this is very messy and kind of roughly written, so I really encourage you to take a look at the math guide that's posted on Piazza for this, because it's all neat and tidy and it actually has examples. Okay, so there we go. That's not bad. So now I can have, if I only had the direct pointers and a single indirect pointer, then my total file size at that point would be the sum of the amount of memory I can access by both types. So 4 megs plus 48 kilobytes. But yeah, what if I had like a 56 megapixel camera? It's not going to fit in, and my pictures aren't going to fit in that file size. Like, if I were to go and acquire a film right now off of BitTorrent, I wouldn't accept anything other than Blu-ray HD, or not, I don't even get Blu-rays anymore. Everything I acquire is 4K HDR. So you're looking at 30 gigs, so we can't fit this here. So we're going to have to use our double indirect pointer. So how much memory can we access via a double indirect? So remember, this is a pointer to a block of pointers to a block, each of those two blocks of pointers to data. So I'm going to give you the general formula here first. It's the number of double pointers in the inode multiplied by the number of pointers in a block squared multiplied by the block size. So in our example, we have in our inode, we have one double indirect pointer, and each of our blocks can contain 2 to the 10 pointers. And then we multiply that by the block size. And so what we end up with here is our file size as accessed from just one double indirect pointer is 4 gigabytes. So if I had direct, the 12 direct in my inode plus one single in my inode plus one double in my inode, then my total file size, my maximum file size would be 4 gigs plus 4 megs plus 48 kilobytes. That's pretty good. Still doesn't fit my 4K HDR copy of anything. So now what? Well, now we use the triple indirect. And hopefully you're starting to see a pattern here in what's going on. So for our triple indirect, that is going to be a pointer to a block of pointers. I'm getting really lazy in writing this now. So we have a pointer to a block of pointers to a block of pointers to a block of pointers to data. And our general formula here is going to be very similar to the ones above, which is the number of triple pointers in the inode, which is usually 1, multiplied by the number of pointers in a block cubed, because there's 3 pointer blocks, right? And 3 levels. And then multiplied by the block size. And if we use the example then from the notes with our node, we have 1 triple indirect pointer, and then we're going to have 2 to the 10 pointers per block, so it's 2 to the power of 10 cubed, multiplied by the block size, which is 2 to the 12. So that gives me 2 to the 30 times 2 to the 12. So I end up with 2 to the 42, which is about 4 terabytes. Woo! Now we're talking. Now I can store a file. Finally, my 4K HDR file fits. When I eventually get a 28K HDR file, it won't fit. Okay, so then our total file size, or our max file size, is the sum. So we've got 48 KB plus 4 megabytes plus 4 gigabytes plus 4 terabytes. And that is our maximum file size. So this is pretty cool. For a 256 256 byte inode, I can actually keep track of a file that's over 4 terabytes in size. My disk is only 256 kilobytes, so who cares? But there you go. So that's pretty neat. Now, something to keep in mind is that if you're looking at this, so let's go back to this, scrolling the wrong direction. If you look at this picture again, that's just keeping track of how much file data. So this inode that we've described can have a file that's over 4 terabytes in size. But the thing that we haven't taken into consideration that is technically a part of this is the amount of space that all these data block or these pointer blocks take up. They do take up space. I mean, think of it this way. Have you ever wondered why when you go to something like Finder or whatever you have and you say get info, there's something called size and size on disk. And look at this. So my file size for this image is 6,707 bytes. That is the actual number of bytes of file data I actually have. But on my disk, that file actually consumes 8 kilobytes. And if we look at another one, let's look at this shell script. It's only 87 bytes, but on disk, it's 4 kilobytes. What's going on? Let's try another file. I'm trying to find a big file. Oh, I know where there's some big files. Here we go. The movie directory. So, here we have a file that is 3,509,229,743 actual bytes. But on disk, it's actually 3.52 gigabytes. So this one actually contains, it looks like about 11 or 12 extra megabytes of data. What's going on there? Well, what's going on there is two things. And I mean, we just saw proof of it here looking at this tiny little shell script file. Remember how I said files don't share data blocks? This file is 87 bytes, but it's 4 kilobytes on disk, which means my block size on this disk is 4 kilobytes, and it's not being shared. So even though I registered as 87 bytes, it's really 4 kilobytes. So that's part one of why the file size doesn't match the size on disk. The other problem is that when we look at something like this big movie file here, you would think that there would only be a 4 kilobyte difference between the size on disk and the actual size of the file. But there's not, because this file is so big, it has to start using extra data structures in order to store the pointers. So the file size on disk, let's go back to our slide here, is actually two things. It's the fact that data blocks aren't shared, but it's also, more importantly, going to include all of these pointer blocks or whatever auxiliary data blocks are used to help keep track of all the files data. It's pretty cool, eh? So you should actually be able to compute now, as just an exercise, if we have a maximum size file for this inode, how much memory is used just in the pointer blocks? And do you care? So that's an interesting exercise for you to do, by the way. All right. So some of that math, by the way, is actually in the slides. And the formulas, of course, are all on Piazza. Okay. So that's fun. Now you know how big your files can be. So now I want to change and talk about how do you actually access these files. How do we access them? So let's suppose I now want to actually implement open. So what I want to do is I want to open the file and read from the file foo bar. Now I give open a path. And what we're going to have to do is we're actually going to have to traverse the namespace tree to find the I number for foo bar. But in order for me to traverse the namespace tree, I have to first know the I number for the root, because I need to actually read the file data for root to get the hard link to foo. So let's follow along with this example of all of the disk reads and writes that are going to happen just to read from the file foo bar. And I think it's going to blow your mind as to how many disk accesses are actually happening just to do this very simple task. So open foo bar. So the first thing I need to do is read the root inode. Now, the root I number is going to be a part of the metadata for the file system. So the operating system is actually going to know what I number corresponds to the root, because we need to know that so that we can actually traverse the tree. So I read the root inode. Now, when we say we read the root inode, that's actually kind of a simplification of what's actually going on here. Because remember, the inode is only 256 bytes, and we're not allowed to read anything that's smaller than a block. So when we say we are reading the root's inode, what we're actually saying is I am reading the block that contains root's inode. So we read it in. When we read in root's inode, it's going to give me a pointer to root's data. Now, we're going to make the assumption that directories, you only need one direct pointer for that to access their data. So I read root's inode and it gives me a pointer to root's data. So then I read root's data. When I read root's data, I'm going to find the hard link for foo. When I find the hard link for foo, it means I get foo's I number. So the next thing I do is I read foo's inode. By reading foo's inode, I'm going to get the pointer to foo's data. So I read foo's data because foo is a directory and I'm looking for bar's I number. So I'm then going to read foo's data to get the I number for bar. It's 4 reads already. Now that I know the I number for bar, I'm going to read bar's inode. But when I read bar's inode, I'm actually going to do a bunch of other things. I'm going to first, after reading bar's inode, I'm going to check the permissions to make sure that the user that has called open on foo bar actually has the correct permissions to open and read bar. Then I am, of course, going to get the file descriptor, and I'm going to add it to the process's file descriptor table. And then I am going to add the file to the kernel's list of open files. And if it's already in the kernel's list of open files, I'm going to update that entry to indicate another process or another thread has that file open. So all of that is done just to open the file. It's 5 reads, 5 separate disk reads. If each of those disk reads takes 25 milliseconds, starts to add up. But if you're ever sitting there wondering why your disk light flickers on so much, I mean, the truth is your disk light can't actually keep up with the amount of flickering that needs to happen. Now, to read the file, we are going to need to start reading for the data from the file. We're going to read the inode again. Now, this is making the assumption that we don't cache the inodes. Real operating systems are going to cache the inodes so that we don't have to keep going to disk. But let's make the assumption right now that we don't cache inodes. If I don't cache the inode, then when I call read, I need to read that bar's inode in again so that I can match the current file position from the file descriptor table to the information about number of blocks and the pointers in the inode so that I can figure out which pointers I need to use to read from the file data. Now, since I just opened the file, the position is 0, so I know I'm going to use the first direct pointer from bar's inode, and then I'm going to read bar's data. Now, since I have accessed bar's data, and bar is an actual file and not a special directory file, I actually need to now update the inode for bar to indicate somebody accessed its data. And so at the end of every read, there is a write to the bar inode to update the last access time. Now you notice we didn't do that to the directories because we don't update access time for directories. We only update access time for data of true files. If we only ever look at the inode for a data file, then we wouldn't need to write the inode unless we were modifying the inode. If we're just reading the inode, then we don't look at file data, then we don't need to write the inode after. And now each read after that, every single read, assuming no cache, is going to read bar's inode from disk, then read the data block from the disk, and then write the inode back to disk. So even a simple read operation, you're looking at a minimum of 3 disk operations. So reading and opening files is actually really expensive. A comment on Twitch is the disk light is a lie. Well, I mean, the disk light is going to indicate to you that the disk is in use. Like I'm currently doing something, but I want to say that I don't think the rate that the LED flickers at necessarily corresponds to the number of IO operations actually happening. Because I think you'd probably kill the LED if it did. I don't think the LED responds that fast. But anyways, it doesn't matter. My disk lights never work, so. And it's like, if you have an Apple, it's like, there isn't even a disk light. Now, if you have one of these lovely Surfaces, by the way, there is a disk light. You just have to look in the back of it. Found that out the hard way one day. All right, so that's opening and reading a file. What if I want to create and write to a file? Even more I/O. So let's now pretend foobar doesn't exist and let's create it. So I call create, which is really just open with a special flag that indicates if the file's not there, create it. So it's going to start out the same way as open, where we read root's inode to get the pointer to root's data to get the I number for foo. Then we read foo's inode to get the pointer to foo's data to get the inode for bar. But bar isn't there, so we're going to create it, which means bar doesn't have a hard link. There's no I number for it. So I need to find an I number. And I'm going to find the I number by reading the inode bitmap, finding a free inode, and then taking it and writing the updated bitmap back to disk. And now I have an I number for my file bar. So I am going to add then the hard link to foo's data. So now bar maps to the I number I just got. The next thing I'm going to do is I'm going to read bar's inode. Now this is the thing that confuses everybody, is they don't understand why we have to read bar's inode before we write it. Remember this, an inode is 256 bytes. We cannot access byte level addresses on our disk. We are only permitting block level addressing. So what that means is that when I want to create bar's inode, that would represent a partial block update. So I actually have to read the entire block that contains bar's inode so that I can then make the update to those 256 bytes. So I will then read in the block that contains bar's inode. I will then create bar's inode where it belongs and write that whole block back to disk. Now, since I have modified foo, I added a hard link to foo, I am also going to write foo's inode because I want to indicate that foo has changed. So in order to create file foobar, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 disk IOs. 10 to create something that's not even very deep in our hierarchy tree. 10. That's crazy. Now you see why we do disk head scheduling. Now you see why we care so much about the IO costs. Because when we are even doing a simple operation like creating a file, it's going to actually cause us to do a lot of IO ops. Now, after I've created this file, I want to start writing to it. And again, we are making the assumption that our inodes are not being cached. So for each write operation, I am going to read in bars inode. I'm going to check the current position in the file descriptor table. And I say, oh, the current position is 0. Oh, okay, I want to write a whole block of data? Cool. I don't have any blocks yet. So once we discover in the inode that we don't have enough blocks to actually add this write to, so we can't append this to any block, I need to get a new data block, which means I have to read the data bitmap, find a free block, take it and write it back to disk. Then I can write to the data block on disk, and then I update the inode to include the pointer to the data block and modify the file size and the file modified time. Write that all back to disk. So to add a new data block to a file, you're looking at a minimum of 5 IO operations. Minimum. For the read, the minimum is 3 IOs. Minimum is 3. That's for a direct pointer. What about a single indirect pointer? So let's suppose I have already exhausted my direct pointers and I want to start adding more data to the file, and it's going to be the first time I need to use the single indirect pointer. Then instead of getting 1 data block, I actually have to get 2 data blocks. Now, I can probably get both of those things from the data bitmap at the same time, but I still have to actually write to the pointer block. So I would have a minimum of 6 IO operations. What about double? Now instead of getting 1 pointer block, I need to get 2 pointer blocks, and I need to write to 2 pointer blocks in the worst case for a double indirect pointer. So now I've got 7 IO operations. What if I have a triple indirect? Then I could have 3 pointer blocks I need to get and 3 pointer blocks I need to write to. So now I'm looking at like 8 IO operations just to write a little bit of data. So hopefully this really stresses to you just how important it is to have the operations on your disk be as fast as possible. Like, we really want to do the disk head scheduling to make sure we are minimizing the costs here. Okay. Now, a lot of people ask me about delete. We don't have delete in the notes. When you delete a file, if you just call rm, you don't actually delete the data. What you actually do when you delete a file, when you remove that last hard link, so if I were to delete the file, I would be removing the hard links to the file. And then so the file is no longer accessible from the namespace tree. So that path will no longer work out. So that's one thing I'll be doing. Another thing I'm going to do is I'm going to open the inode bitmap, and I am going to mark that inode as free. And then I'm going to open the data block bitmap, and I'm going to take every data block that belongs to that file, which I can get that, of course, from the inode before I mark it as free. And then I am going to mark all of those data blocks as free. But I do not erase the data in the inode, and I do not actually erase the file data. That is a basic delete operation. A basic delete operation simply removes that path from the namespace tree and marks the inode and data blocks as free. It doesn't actually clear your data out. And if you're doing something like a quick format of your disk, quick format, you want to know what it does? It takes the inode array, the bitmap for it, and it marks everything as 0, so free. And it takes the data block bitmap, and it marks all those bits as 0. That's it, you're done. Disk is empty. All the data's still there. Don't quick format. Don't do it. Bad things will happen. If you actually wanted to do a low-level delete, you actually have to visit every data block and clear every single one. And it's going to be a lot of work. And my understanding of traditional hard drives is if you want to actually make sure that the data can't be recovered, you actually need to do it 7 times. You have to overwrite it at least 7 times. Otherwise, people will still be able to recover what was there. Fun things, eh? All right. So that is a Unix style, kind of like ext1, ext2 file system. But there have been many, many other different kinds of file systems, and I want to quickly discuss one with you called chaining. Chaining is really exciting. So this is the idea where we're going to store our file as a linked list. It's very easy, very, very, very easy. So what we're going to do here is we'll have some master table of inodes that says, okay, here's a pointer to the first block of your file data. But that's all they have, metadata and a pointer to the first block. So if we look at the yellow or the purple file here, so the purple file's first block is right here. And the very last 4 bytes of this data block will actually be a pointer to the next block. And the very last 4 bytes of this block will be a pointer to the next block. It's called chaining because it makes a linked list. Now, here's some interesting facts about the chaining-based file systems. Random I/O is terrible. The nice thing about random I/O with very simple file system, the file system we just looked at with inodes and single indirect pointer blocks, is even if you were trying to do like random access, there is a cap, like a hard cap on how many blocks you're going to have to read. So if I want to read the very last byte of my giant 4 terabyte plus file, and I already have the inode for the file, then I read the inode, like I already have the inode, I read the inode, I read 1 triple block, 2 triple block, 3 pointer blocks, 4 data blocks. So it's 5 reads to get the last byte of the file. That's great, right? With chaining and random I/O, trying to get the last byte of the chain, well, I would actually have to read for every byte of my 4 terabyte file in order to get to the last byte of my 4 terabyte file. So random access with chaining, very bad. Now, sequential access with chaining, not a problem, because if you are already going to read every byte in order, then just do it with this. One of the advantages, so it's acceptable for sequential access, and one of the advantages if you were just doing sequential access is the fact that you don't have all these blocks of pointers. So each data block would have 1 pointer to the next block. And if you look at how much extra data that's using, it's not that much. In fact, it would be significantly less than what we're using for our Unix style file system. So, I mean, random I/O really bad, but sequential I/O is actually pretty decent for a chaining file system. Now, Microsoft, and I'm not sure if Microsoft is actually the people who invented this, but there's this concept of storing the chain externally. So what if you wanted to improve file access time so that you didn't have to actually read the file data to get to the end of the file? So they wanted to take the chain and make it external to the actual data blocks. So they called it external chaining. So at the beginning of the disk in a file access table, i.e. FAT, file access table, FAT, they're actually going to store the chain. And it's simply going to be kind of like, here is a teeny tiny entry for each of the data blocks, and then your inode has a pointer to the first. We'll have the address of the first thing in the chain, and then these just have numbers in them. So this takes up very little space, and now following the chain is much, much faster because you're reading through much less data to actually follow the chain than actually chaining through this. So we'd actually have like this here would have the index to the next block in the chain. So each one of these little nodes is going to have the index of the next block and the actual index of the data block. So it stores very, very little information. So this is actually the FAT file system that's been used in Windows. So FAT16 and FAT32 are actually an external chain. And so that's going to give you a bit better random I/O. Maybe not as good as our Unix style file system, but you still get the nice benefits of sequential access. This is still really fast. And the amount of extra data that's being stored is actually, again, less than the Unix one is storing. Now, Windows actually used the FAT32 file system for a really, really long time, and FAT16 before that. There are some restrictions. So FAT32 has a maximum file size of 4 gigabytes. And if that's a problem for you, there is an extension to it called exFAT, which lets you do bigger ones. But this file system is so easy to use, and it's pretty decent for things like if you're just playing media files, it's okay. That if you look at a lot of devices, like things like your cameras, a lot of cameras are either using FAT32 or exFAT as their file system. Things like Blu-ray players, if they understand that, your TV understands FAT32. FAT file systems are probably the most universally understood file system out there. They're so easy to work with. Like my car, we actually had a TV system installed in it for the kids, and it understands FAT, but it certainly doesn't understand NTFS. It's just so easy. So this is chaining. There is another kind of file system that we used to talk about, but we're not going to, and that is log structured file system, and that's what Amazon S3 is actually based on. And I recommend you actually take a look at that if you have some time. Now, we've got a few slides left here, and I don't really want to push the time. So what I'm going to do is I'm going to end that here for today. And then in our next class, so tomorrow is going to be our Dr. Stallman talk. And then Tuesday, our episode 23 is actually going to be, we're going to finish off file systems. We've got some lovely sample problems for you to do, we'll walk through you. And then we're going to kind of do a wrap up review by talking about virtual machines. That's going to come back and touch on all the topics that we've talked about so far. So that'll be our next episode. And then we'll have something special planned for episode 24. Because you've paid for 24 episodes, so I better give you 24 episodes. It will be OS related. So we will see you tomorrow, hopefully, for Dr. Stallman's talk, and then we'll see you next week for episode 23. And for those of you, by the way, who are wondering if you can't actually attend the live stream, will you still be able to watch it? Yes, it is supposed to be recorded, and then we will make it available to you afterwards. It is not being posted to YouTube or Twitch or anything like that because those are non-free things. But we are going to be posting it to possibly hosting it off the CS Club and Archive. So we will make sure that it is available to everyone. All right. See you tomorrow.
Hello, I'm a Mac.
And I'm a PC.
What's with the big hand?
Well, I figured it's time to show the world my position.
Really? Well, that's what I was trying to do with this ultra-hip t-shirt I designed on iLife.
Number one. Don't want it goofing off.
PC. Such a whiz with those numbers, you know that we can't both be number one.
I was here first.
That's debatable. No, let's not argue about it. I mean, we're the only guys in town. Check us out. Look around, there's nobody else.
You're right. No one else.
No one.
Hi, I'm Linux. And there are an estimated 30 million Linux users out there.
How long have you been standing there?
Long time.
Boy, you sure grew up fast.